right. Whoa, it's a little loud. So we're continuing on with our discussion of stereoisomers, and we're trying to define this term enantiomer. Last time as we talked, we were describing the concept of chirality, which is a molecule that is not the same as its mirror image, and we were talking about how to evaluate that. The idea is that you need to get good at manipulating molecules on the page, and it may require working with the model set to get to that point. But the idea is if we spin this molecule around, it becomes very easily the molecule on the right. So this molecule is the same as its mirror image. Go ahead.
What is the difference between chiral and enantiomer?
Chiral and an enantiomer. One is, let's see, so parts of speech, right? Chiral is an adjective, refers to not being the same as your mirror image. Enantiomers, an enantiomer, that's a noun, and that refers to a chiral molecule that is not the same as its mirror image. So it's correct to say that two enantiomers are each chiral. Enantiomer describes a relationship between two molecules. In other words, it doesn't make a huge amount of sense to ask, is this one molecule an enantiomer? To what, right? So it's enantiomer is a relationship between two molecules that are not the same, but are mirror images, and the two enantiomers themselves are chiral. So an example of a chiral molecule that I sort of referred to last time might be a molecule with an sp3 hybridized carbon and 4 different groups attached to it. I'm not claiming this molecule exists or is really stable, but it is an illustration of chirality, because we're going to see that these two are not the same as each other. And maybe we'll use different colors to label the different groups to facilitate discussion. I'll choose maybe purple here. All right. So again, one of the manipulations you could do on paper to help you think about structure is the claw manipulation, where we're simply going to spin around. We're going to grab a hold of one part of the molecule and spin around by about 180 degrees. And when we do that, that should give us, these 3 lines indicate that what we're going to draw is here is the same as what's above, should give us, let's see, this view of our molecule. When we swing around 180 degrees, chloro on the left comes over here on the right. Hydrogen, of course, stays exactly where it is because we're grabbing onto that and spinning. The bromo in the back, though, is going to spin around to the front, and the fluoro in the front is going to spin around to the back. So that's actually pretty important that you be able to see that. Questions? Okay, so just be thinking about that in terms of how you visualize molecules. Now we compare and see, are these the same thing? The answer is no. You can line up the hydrogen and the chloride, but the fluoro and the bromide are in different places. And you could spend eternity trying to line these two up, and they never will. So these two molecules are, we will say, enantiomers of each other. So there's two basic issues here. First, is a molecule chiral? The way you determine that is you draw its mirror image and you see if they're the same thing. The second issue is, are these two molecules enantiomers of each other? And the way you determine that is you see if they are mirror images of each other, but are nonetheless not the same thing. Okay, so we're going to call, let's see, a classic way that a molecule can be chiral is if it has an sp3 hybridized carbon attached to 4 different things. And we're going to have a special term for an sp3 hybridized carbon attached to 4 different things. And that is, we're going to call that a stereogenic center, or for short, a stereocenter. Some people, in particular, some older organic chemists and then some folks in biology will refer to stereocenters as chiral centers because they're carbons that make the molecule chiral. Technically, chirality depends on the overall shape of the molecule itself, and it is possible to be chiral without a stereocenter. I can show you some examples of that later on. So I tend to avoid the term chiral center, and if I hear somebody say it, it makes me twitch just a little bit, and then I get over myself and move on. But stereocenter is the word we're going to use. Now, we're going to need a way of talking about which enantiomer is which, right? Because these molecules would have the same name in terms of the connectivity. Bromo, chloro, fluoro, methane, or something like that. But they're different, and so we need a way of talking about that. And to do that, we're going to use the R versus S system, which is going to be exactly like the E versus Z system, except we're going to apply it to a stereocenter. All right, so to talk about R versus S, we need to assign priority to all the groups that are attached to the stereocenter. And we're going to do this exactly like we did with E or Z. The first question is, which is the heaviest of the atoms and which is the lightest of the atoms attached to the stereocenter? Remember, it's not the overall weight of the entire group that's attached, just the atom. So we're going to compare, in this case it's pretty easy, hydrogen, fluorine, chlorine, and bromine. Hydrogen is the lightest, it should have priority 4. Bromo is the heaviest, it should have priority 1, and then chloro 2, and then fluoro 3. All right, now we're going to have to, this is fine because this view of the molecule is the least useful one possible for assigning R versus S. What we're going to do is we're going to do the shove operation on the hydrogen. By that we mean shove it back into the page. If we were to do that, let's see, I'm not sure how to. Shove. All right. Force push, yes. Maybe air quote sort of motions around that. Anyway, that's going to tip the hydrogen back. Chloro is still going to be here. Bromo will tip up here. Fluoro will be here, and hydrogen will be there. If it's helpful, we can continue to color the groups. Take a minute and look at that and convince yourself that we actually indeed did not change any bonds, we just moved the molecule. Just tipping it over. I like force push better than poke. I guess it could be poke on the hydrogen. All right, so we've got priority 4 in the back. 1, 2, 3 here. Going to draw an arrow from 1 to 2, from 2 to 3, and from 3 back to 1, with 4 going away from us. And we're going to note that that is a clockwise direction. And therefore, we're going to call the stereocenter R. R for Latin rectus, which means right, I guess. So this stereocenter would be called an R configuration. It would have the R configuration. You're going to put this at the front of a name in the same way that you would E versus Z. Now, if we know that these two are enantiomers, because they're mirror images of each other, and if we know the configuration of one of those two, if the stereocenter in one of those enantiomers, we automatically know the configuration of the stereocenter in the other enantiomer, because it's opposite. Though, if you want, you can verify that. We'll do force push on this molecule, and we'll have fluoro here, bromo here, hydrogen here, chloro here. And again, we can assign priority groups 1, 2, and 3. And you can see if we draw an arrow with, from 1 to 2, from 2 to 3, and from 3 back to 1, and 4 is going away from us. This is a counterclockwise rotation, and so we're going to call this S, which is Latin for sinister or something like that, which I guess that teaches us that southpaws are evil. Is that what we're learning today? I don't know. If you're left-handed, I don't actually think you're evil, but actually that is the Latin term for sinister, is the Latin term for left. But we've already talked about left in Spanish, izquierda. That'd be nice if we could use the I. Anyway. Okay, any questions about assigning E versus Z? I mean, sorry, R versus S? Go ahead.
Going back a little bit, can you explain again the chiral, enantiomer, and stereocenter?
Okay. Chiral, enantiomer, and stereocenter. Chiral is an adjective describing a molecule. A molecule is either chiral or it is not. Okay, that's true for all molecules in the universe. They are either chiral or they are not. There's no other choices. And a chiral molecule is not the same as its mirror image. Two chiral molecules that are mirror images of each other, but are not the same, are enantiomers of each other. So an enantiomer is a specific kind of stereoisomer. An enantiomer has, two enantiomers have the same molecular formula, same connectivity, but are not the same, even though they're mirror images of each other. All right. Follow-up questions? Yes?
So not related to that, but for this numbering here, the lowest priority group is always pushed to the back, and then from there you just number counterclockwise or clockwise, right?
That's right. The way we're choosing to assign R versus S is that we put the lowest priority group 4 in the back. I'll show you what to do if you don't want to do that. There's a shortcut.
Show us.
Yes. All in good time, young Padawan. Yes.
And I was actually just about to ask, somewhere I had heard that like if the hydrogen was coming towards us, then you do whatever you're supposed to do and you switch it.
Yep, if the hydrogen's coming, that's the secret. That's the secret. If the hydrogen's actually coming out towards you, then you just do this, but switch it. Do it backwards. I'll give you an example of that. Yeah. Go ahead. Yes.
Does this only work for tetrahedral molecules?
Does this only work for stereocenters where we have a A tetrahedral molecule, I would say no. Any molecule that has an sp3 hybridized carbon that is attached to 4 different things, you can do this with.
And does it always work out that it's always 1, 2, 3, 4? Or is it sometimes like 1, 4, 2?
No, you can always assign, if it's a stereocenter, you can always assign priorities 1, 2, 3, and 4.
Meaning, is it always going to be very neatly clockwise or counterclockwise?
Is it always going to be neatly clockwise or counterclockwise? Yes, if you have the right view of the molecule. So an example of when that's not the case, here I have the highest or the lowest priority group just in the plane of the page coming up. Now if I'm really good at visualizing things, I can sort of lean down into the page, right? Bromo, chloro, fluoro, okay, now I look like Dr. Strange, but less cool. And that's clockwise, so it's R. You can always do that, it's just sometimes harder, and you gotta be good at 3-dimensional reasoning. Yeah? If there's a lone pair, that's a great question. If there's a lone pair making it sp3, would you not be able to do it in this case? The answer is it depends. So the question you might ask is, can nitrogen be a stereocenter? Usually not. I know you hate that I just said usually, because you're like, when not? And the answer is it's complicated. So here's a nitrogen that's technically surrounded by 4 different things. Is that nitrogen chiral, and can you assign a stereochemical configuration? If the nitrogen stayed like this, the answer would be yes. However, it's pretty easy for the nitrogen to go through an sp2 hybridized sort of transition state and then invert such that the lone pair is on the bottom. You can do calculations that show how easy this process is. It's not a huge energy barrier. It happens readily at room temperature. And so, no, in that case, I mean, if you cooled it down so that, but in this case, no, you wouldn't assign the nitrogen as a stereocenter. Now, there is, however, there are atoms that don't invert like this very quickly. I'm going to show you the structure of one because I'm sort of nerding out here. I need to reassure you that you don't need to memorize this structure, nor would I ask you to assign R versus S for this molecule, but it's worth just showing you. What I'm going to draw for you now is the S enantiomer of the drug omeprazole. If you go to Costco, they are selling this by the kilo, or at least in very large bottles, and this is used, it's a proton pump inhibitor. It's used to decrease heartburn, stomach acid, among other things. This is the stereocenter, and that sulfur, so you're already looking at that, whoa, it's surrounded by it's got more than 8 electrons around it. Yes, that's fine for larger atoms. It's got a lone pair, an oxygen, a carbon, and another carbon, 4 different groups. And the sulfur doesn't invert as fast as the nitrogen does, and so that is a stereocenter. We'll mark it with this for stereocenter, and you can choose the configuration, which would be S. Though you have to, how do you even indicate whether the lone pairs are going back into the page or not? And the answer is, I don't know. There's got to be some way to do it, but in any case. So don't worry about that, but yes, you can be, one of those 4 things can be a lone pair in the wild world of molecules. We're going to be only worrying about carbon-based stereocenters for the most part. Okay, other questions?
So
We don't need to know what priority the electrons would have. Well, if you want to know, it's 4. Yep, but you don't need to know that. Yes?
So let's say a molecule has 2 stereocenters, and one hydrogen's coming at you and the other hydrogen's going into the page.
Yeah.
Would you still manipulate the one that's coming out of you to put into the page or no?
Okay, that is an excellent question. I am glad you asked. Let's look at a molecule like this. Does that maybe describe a situation you want to see? Ish? Okay. All right, first, we can go ahead and find out if there are any stereocenters in the molecule. And to do this, you simply look for carbons that are sp3 hybridized that are attached to 4 different things. And they have to be any difference, well, how do we say this? 4 different things counts for any difference that's out there. In other words, it doesn't matter that these 2 are carbon. There would be a tie there, and you go on to the next atom and the next. These 2 groups overall are different, and so that carbon is still a stereocenter. But with that in mind, we have, maybe we'll call 1, 2, 3, 4. We've got on carbon 2, oh shoot, we're numbering the carbons, but we're also going to be doing priority groups. So maybe we'll just call this A and this B. On carbon A, we have 4 different things. Same thing on carbon B. If we were going to assign stereochemical configuration to carbon A, we would compare all 4 groups attached to that carbon. We've got an oxygen, a hydrogen, and 2 carbons. Right away, we can say the hydrogen is 4 and the oxygen is 1. In between the 2 carbons, it's a tie, so we have to now ask what they're bonded to. This one is bonded to 1 other carbon and 3 hydrogens. This one is bonded to 2 other carbons and an oxygen and a hydrogen. The oxygen comes first in our list. We go down atom by atom. Oxygen wins. This group is 2 and this group is 3. Follow how we did that? Then get your sling rings on. 1, 2, 3. And that is a clockwise rotation. And your priority 4 group is in the back, so we're going to call that stereocenter R. Okay, now I'll redraw the molecule and we'll do the same for the other stereocenter. And using the same sort of pattern, this is 1. I'm concerned that that's not very clear. All right, so oxygen is 1, proton is 4, this ends up being 3, and this ends up being 2. Draw our line 1 to 2, 2 to 3, 3 back to 1. Now, the only problem with all of this is hydrogen's in the front. So we can say, okay, it's clockwise rotation, but priority group 4 is in front. Therefore, instead of R, it should be S. Now, if that doesn't make sense to you, and I'm not sure I can do this. If you go clockwise and then continue the same motion but go behind it, it turns counterclockwise. Okay, we're still, yes. Front and back reverses clockwise versus counterclockwise. To prove to you that this is the case, we can, if you want, tip this molecule back using our force push action on the stuff in the front. And what will happen when we do that is The hydrogen will go in the back. The oxygen will come out front. The other part of the molecule is here. This is carbon B. Again, we'll continue to go 1, 2, 3, 4. And you can see, 1 to 2, 2 to 3, 3 to 4. That's counterclockwise. Hydrogen prior to group 4 is in the back, and so we could say again that it's S. Yeah? All of you were, sorry. Same question? Different questions?
We'll find out.
Okay.
Are these not chiral? I mean, they are chiral because you put it in here, one would be R, one would be S still.
So you're asking,
Is that molecule chiral?
is this molecule chiral? We don't know yet. A molecule can have stereocenters and not be chiral. So you have to compare it to its mirror image. So go ahead.
I was just gonna ask, so if the hydrogen or the 4 priority group is in any location except to the back, you're gonna do the opposite. Like even if it's on the side.
So the question is, if the hydrogen is in any location except the back, are you going to do the opposite? It's tricky when it's on the side. Oh man. The reason it's tricky when it's on the side, and I'm making stuff up at this point. I don't even know what this should be. Okay. If you're good at putting your eye in the plane of the page, that's a weird eye. I'm going to try that again. If you're good at putting your eye in the plane of the page and looking down the carbon-hydrogen bond, sort of drawing a pseudo-Newman projection with the hydrogen in the back, then that can be totally fine. And then that makes it quite a bit easier. 1, 2, 3. So we'd say R. I don't know that it would be easy to do that from this point of view, but if you can, great. As long as hydrogen is in the back relative to how you're looking at it, though, you go with the regular rule. Okay?
Your pseudo-Newman doesn't match the molecule. Yeah.
Yeah, it does. Thank you. Thank you. Yes, sorry. See, I'm not good at that. That's why I would have redrawn the molecule. So, yes, from that perspective, OH is here, methyl group is there, ethyl group is there. 1, 2, 3. S. Is that better? Yes, okay, go ahead.
If also a carbon only counts as a stereocenter, it has 4 different groups attached to it. So like if it had 2 hydrogens attached to it, that's 10.
That's right. If a carbon has 2 hydrogens attached to it, 2 of any of the same thing actually, it doesn't count as a stereocenter. And you'll be able to tell because you'll try to assign R versus S and you'll get stuck on, is this 2 or 3? And the answer is it's neither. This is not a stereocenter. Yeah?
So in the molecule that you have on the top left, do you have to assign Stereocenter designation to the other carbon as well?
So do I have to assign stereocenter designations to both of these carbons? Yes. So these are the same molecule, I'm just doing each stereocenter separately. But if we were gonna draw the molecule this way, this way. This stereocenter is R, and this one is S. Yeah?
So what would the name be of the whole molecule? Where would you put the R's and S's?
So you would number the carbons. This is going to be a butane diol because it's got 4 carbons and 2 alcohols, and those are the highest priority functional groups. So butane diol, and it would be 2,3-butane diol, and then in the front, you're going to put the stereochemical configuration. and I guess we can choose 2R versus 3S. How did I know to do it this way? That is an excellent question. I'm glad you asked, and you're going to see that it doesn't matter here because this molecule is not chiral. Boom, boom, boom. I'll show you that in just a second. But in general, yes, that's what you do. You take the numbers and the stereochemical configuration for each stereocenter and put them at the front. Okay, others? Yes?
So you don't need to put E or Z if you're doing progress?
E or Z you would put if there's a double bond in the molecule. And there may very well be molecules with pi bonds that you need to assign E or Z and R and S. And you'll just put any and all of those stereochemical designations out front.
Put R and S first.
Would you put R and S first? I don't know. No idea. Mostly I just ask you to assign R versus S on exams. And you think, or it's usually three options. It can be R, it can be S, or it can be, that is not a stereocenter. So you'll want to make sure your process is good for assigning R versus S. As you're practicing, it is possible to get the, when you got a 50-50 shot, it's possible to get the right answer and still not actually know anything. And so you want to make sure you've practiced and you're getting the right answer for the right reason. Yeah?
How often is it actually this is not a stereocenter? Because I feel like sometimes teachers put it out in exams.
How often is it this is not a stereocenter? Well, what is this carbon? What is the configuration of this carbon right here? That's its hybridization. I asked for its stereochemical configuration. Is it R or S? Ha, not a stereocenter. Would I put that on the exam? I am totally capable of putting that kind of thing on the exam. Yes. Okay, now, the question we want to ask is, or what I want to show you is that there's a difference between having a stereocenter and being chiral. The molecule I have drawn has two stereocenters, but we're going to try to see, is it the same as its mirror image? So to do that, I will draw the molecule again, and we will put our mirror here, and then we're going to draw on the right a reflection of what's on the left. And now we're going to see, are they the same thing or not? And at first glance, if you do this, you might think, well, it doesn't look like they're the same. This is where you've got to get some really good spatial reasoning. I'm going to show you a couple of ways that you could demonstrate to yourself that these are indeed the same thing. First is we've talked about the claw operation, the force push operation, and now we're talking about the pancake flip operation. We'll just color because, let's say, yeah, stylish purple-handled spatula. So you slide that spatula under the molecule and you're going to flip the pancake 180 degrees. When you do that, the chain is going to look like this instead. OH, which was here, pointing towards the top of the page and out towards us, will now be pointing towards the bottom of the page and away from us. OH here, which was pointing towards the bottom and away from us, when we flip it over, is going to be pointing towards the top and towards us. And lo and behold, whoa, they are the same thing. All right, another way you could realize that they are the same thing is to try to rotate around this carbon such that you arrive at a conformation where the methyl groups are eclipsed with each other. Okay, and you could do the same here. Rotate around the carbon such that the methyl groups are eclipsed with each other. And then, whoa, where'd it go? Spin. Same thing, right? Okay. So what we've demonstrated is a molecule that has stereocenters may or may not be chiral. And as we've assigned these stereocenters, we could call this one R and that one S, and then this one S and that one R. Oh, whoops. I got it exactly wrong over here. And this is why earlier on I was saying that it actually doesn't matter whether we call it 2R3S or 2S3R. The molecule's totally symmetric, so carbons 2 and 3 are equal to each other anyway. All right. Yes?
Sorry, even if it's not chiral, so do we still need to do R versus S?
Even if it's not chiral, do you still need to do R versus S? Yes. Okay, so what we're learning so far, and what I'll generalize to is, if a molecule has one and only one stereocenter, it must be chiral. So I know you guys like rules. One and only one stereocenter. Your conclusion is the molecule must be chiral. It is, which means it's not the same as its mirror image, and the molecule and its enantiomer are the molecule and its mirror images are enantiomers. The molecule must be chiral, and it and its mirror image are enantiomers of each other. And an enantiomer is a type of isomer. And that describes the relationship between two molecules. So it makes no sense at all to ask, is this molecule an enantiomer? Well, sure, it's an enantiomer of its enantiomer, but usually when I ask, usually you'll be answering enantiomer when I ask, what is the relationship between these two molecules? All right? Now, second, we've shown that if a molecule has two or more stereocenters, it might be chiral. But beware. The molecule here has two stereocenters. Nevertheless, it is not chiral because it is the same as its mirror image. So, one of the ways I sometimes trick people is I will ask, what is the relationship between these two molecules? And you'll look at them and you'll say, well, they've got stereocenters and they're mirror images of each other, therefore they must be enantiomers. Not so fast. They are actually the same thing. And the only way you can see that is to play around with their structures until you can verify that they're actually the same thing. Yes?
Is it valid to use the claw on this one? Because I'm looking at it, like, if we just grabbed it on that OH group on the top and rotated it, wouldn't it be the same?
let's see, could we use the claw, you
Is that
mean?
another way of looking at it, or should I do?
Oh, no, that's perfect. That's great. That's a third way that I didn't even think of. The question is, could I have done the claw on grab here and spin around? In so doing, what would that have gotten us? Ching, 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 dun, dun, dun. And then, did I not do the claw? Oh, okay, yes, the claw is still holding on to this. Is that what you envisioned?
It's tricky when you have one that's going into or out of the page to claw. So if you just rotated it, then one would be going in and the other would be out.
Oh, you want to put the claw on an imaginary axis right here? That's sort of the pancake flip at that point, but yeah. But basically, what you do is you ask, if I built a model, could I demonstrate that these two are the same thing? All right, so what I've shown you here is actually a special class of molecules. This is a molecule that has stereocenters, but is its own mirror image, and is therefore not chiral. By the way, the technical term for not chiral is achiral, but I always hesitate to use that term because this is an achiral molecule. Sounds just like I said, this is a chiral molecule. So I'm going to avoid that. We'll just use not chiral. On exams, I also try to avoid confusion by with A and B. I find if you put chiral as option A and achiral as option B, people get mixed up in their brains and do stuff. So yeah.
Just to clarify, they do have stereocenters, and we want to assign R and S, but it's not chiral.
That's right. It has stereocenters. We can assign R versus S, but it is not chiral. And that is a special class of compounds. We're going to call this a meso compound. Okay. A meso compound differs from an a not chiral molecule in the sense that any molecule, not all molecules that are not chiral are meso compounds. In order to be a meso compound, you have to be not chiral, but still have stereocenters. Yeah?
Might be wrong, but if there's one stereocenter and there is two of the groups that are the same, but still, it wouldn't be chiral.
So you were asking if I have one stereocenter, but two of the groups are the same. If two of the groups are the same, that is not a stereocenter. Yeah. So if a molecule has one stereocenter, it has to be chiral. If a molecule has two or more stereocenters, it might be chiral, but you've got to watch out for a meso compound. Now, as to summarize all of this stuff, one way to recognize molecules that are the same as their own mirror images is simply to look for a plane of symmetry in one of the conformations of the molecule. Let me illustrate where that plane of symmetry is here. You see it best when we modify this conformation such that the methyl groups are eclipsed with each other. Then I see easily that what's on the left is a reflection of what's on the right. And when a molecule has a plane of symmetry, as we've tried to show you here, it, by definition, will be the same as its mirror image. Dang it. Let's see, I want this, but I want this. There we go. Ooh, that's lovely. all you have to do to demonstrate that's the case is once you've found the plane of symmetry, slide it over, copy and paste the molecule, and boom. It is the same as its mirror image. Okay? So, one way to avoid falling into the meso trap, which is where I draw two molecules and you're tempted to describe them as enantiomers, but they're actually the same molecule. One of the ways you can do that is to look for a plane of symmetry. But you might have to adjust the conformation of the molecule or adjust your view of the molecule for you to be able to see that. All right, so that's one of my secret evil ways of concealing meso compounds. Another secret evil way of concealing compounds that are not chiral is by, whoa, that's kind of cool, but not today. Not today, Zerg. We're going to draw this. We're going to draw a molecule in a chair conformation. Okay, now, I'm going to tell you that we could go through the exhausting process of trying to draw, I wanted that to be a dotted line, trying to draw a mirror plane, and that's the problem, is you gotta, okay. Oh man, line width is just a problem today. All right, well, you could try to do this, and you would need to have some really good three-dimensional reasoning to be able to show that these two are the same thing. You'd need to spin this around and do a chair flip, and then you could get this. It's much easier to see that these two are the same molecule if you view them both from above. And so this is a trick with cyclohexane rings, or really rings of any kind. It's always easier to tell whether they're chiral or not if you view them from above. So, 1, 2, and so on. Methyl group is up. Other methyl group is up. You can see the plane of symmetry, actually. You can also see that these two are the same thing. Okay? So, trick number 2, draw the molecule from above if it's got a ring in it. That'll help you see whether I'm tricking you. All right, we got more to do on chapter 5. I'll see you next time.